Hello, and welcome to this tutorial for BioXTAS RAW. In this tutorial, you will learn how to do three-dimensional reconstructions with bead models via DAMMIF or DAMMIN in RAW. This tutorial requires a separate installation of the ATSAS programs. It also requires the RAW tutorial data available on the RAW website. If you've already done the genome tutorial to generate a PFR function, and you saved the A/RG truncated PFR function that you generated there for bead model reconstructions, load that in now. If you didn't save the truncated PFR function, or you haven't done that tutorial, you can find such a function in the GI complete folder here, which I'm going to load in. You can see that that loads into the IFTs tab in both the plot panel and the control panel. Please note that for these bead model reconstructions, it is important to use a dataset that's been truncated to about A/RG at the maximum Q. Otherwise, you start including information about internal structures of the macromolecule, and bead models can't fit that, so it ends up trying to overfit essentially the edges of the model, and you get a worse reconstruction. So I've loaded in this truncated function. We're now ready to do a reconstruction. So in order to open the DAMMIF window, I right-click on the IFT, and I select Bead Model DAMMIF DAMMIN. If you don't see this option in the right-click menu, it means that RAW doesn't know where the ATSAS program is on your computer. You either need to install ATSAS and restart RAW, or you need to tell RAW where ATSAS is in the advanced options. So I'm going to click on Bead Model. It opens a window here. So before I get started, I just want to say a couple things about shape reconstruction. So a shape reconstruction for SAXS data doesn't provide a unique reconstruction. If you've watched the ambimeter tutorial, you've already heard this. So essentially what we do is we create a number of these different reconstructions. In this case, we'll do 15. 15 to 20 is a pretty reasonable number in general. And then we'll average those all together, and we'll essentially use the average to create a consensus shape of what it might look like in solution. This particular mode of reconstructions, this dummy atom model or bead model reconstruction, is the most popular, and it typically is done using either DAMMIF, dummy atom model, the F is for fast, or DAMMIN, which is the original, from the ATSAS package. These programs are not native to RAW, and if you use any of these programs in your analysis, you should cite them appropriately. You can see how to do that by clicking on the How to Cite button. There's a number of different programs that we'll use as part of this reconstruction to either make the reconstructions or average them or evaluate them. And so please make sure you cite appropriately. All these are also available on the RAW website. So the first thing we're going to do is we're going to make a new folder to put the output in. It turns out generating 15 models makes a lot of files. So in the reconstruction data folder, I'm going to make a GI DAMMIF folder, which you can see there. We would next set the number of reconstructions. 15 is a reasonable number to use. We're going to do these in slow mode, which is what I recommend for a final reconstruction for a paper. We'll average the models once we're done with DAMMAVER, that's checked. We'll refine the average with DAMMIN, that's checked. I want to align and cluster the resulting bead models as well. And then after all of that's done, I want to align the final output to a known high-resolution structure so we can see how they compare. In this case, that final reconstruction will be aligned to the high-resolution structure for glucose isomerase, this one XIB former. This is I think about a 2 angstrom resolution crystal structure of glucose isomerase that I've packed into the tetramer structure that it exists in solution. We've now got all the settings we want to set checked and done. We could set symmetry or anisometry if we knew it, though it's always good to do a run with no symmetry and no anisometry, just to make sure you're not biasing your reconstructions too much. Now that we're ready, I'm going to click Start. We'll note that you could change the advanced settings if you want. And once I click Start, it's going to start up all the different DAMMIF runs. It'll do however many you've specified here simultaneously, depending on of cores your computer has, this may be more or less than 15. And then once it's finished all these runs, it'll do the average, and then the refinement, then the clustering, and then the alignment. In these tabs, you can see the output from the DAMMIF run as it goes through the simulated annealing process to generate the bead models. And the status window will provide overall status updates as the runs finish and as the next runs start and we move on to the next steps. Once it's done, we'll see the results in the Results tab, and we can view the models in the viewer. Because this takes a while, we're going to take a break here, and we'll pick this back up once we have the results. Once all of the processing finishes, the DAMMIF window should automatically switch to the Results tab, which you can see up here. In the Results tab, you'll see a number of different sections. Some of these sections being shown will depend on what processing you did. So at the top, you see ambimeter results. We discussed ambimeter in a previous tutorial. This is always shown. If you ran DAMMAver, you'll see the normalized spatial discrepancy section. This gives you the average normalized spatial discrepancy, which is essentially the average distance between your different models. It gives you the standard deviation of the NSD, and it tells you how many models DAMMAver included in the average model that it made. If you have a new enough version of ATSAS and you did more than 3 reconstructions, you'll also see the reconstruction resolution section, which is the result from SAXS that you get automatically when you run DAMMAver, and that gives you an estimate of the resolution of the reconstruction. If you ram DAMMClust, you'll see the clustering section. This will tell you the number of clusters. In our case, there's only one because this is a very well-defined molecule and there's not several different shapes showing up in solution. And if you had more than one cluster, it would list all the clusters here, whether or not they are isolated, which means whether they're one model or more than one model in the cluster, the name of the representative model, and the deviation between models in the cluster. If you had more than one cluster over here, you'd see the cluster numbers and the distance between the clusters. Finally, at the bottom, what you always see is a number of tabs here in the Models section. The first tab that we see is the Summary tab. This lists summary results for the models, including the chi-squared of the fit, the RG of the model, the Dmax of the model, the volume of the model, the estimated molecular weight of the model, and the average NSD of the model. Each individual tab shows the data, the fit of that model to the data, and the normalized residual of that model. You can go through this for every model if you wish. You can see in this case they're all quite similar. This is also shown for the refined model here at the end, if you did a refinement. So let me talk a little bit about the different results that we're seeing here now that I've gone over what's available in this window. So the ambimeter results we've already discussed in a previous tutorial. So let's talk about the normalized spatial discrepancy. So the mean or average normalized spatial discrepancy is essentially telling you what's the average distance between models in your reconstruction. You want this to be small, which indicates a very stable reconstruction with really only one shape of model in it. Less than 0.5 is considered quite good. Between 0.7 and about 0.1 is considered fair, and if the average NSD is greater than 1, that usually shows poor stability of the reconstructions, and you probably shouldn't trust that reconstruction. The standard deviation, again, is the deviation of the NSD, how much, what's the sigma on the average. Again, you want this to be small. The number of models included, or how many models were included in the average when it makes the average model. In this case, all of the models were included. If you have a larger NSD, some of the models can be rejected. I think the threshold is any model with an average NSD that's something like 2 sigma above the mean NSD is rejected from the average. If you had a rejected model, or more than one, they would be highlighted in red down here in the Summary tab. Ideally, you want 0 or maybe 1 rejected models. If you have a large number of rejected models, again, that's a sign that you don't have a very stable reconstruction. The ensemble resolution is just an estimate of the resolution of the ensemble. In this case, it's 26. This is fairly low. This is mostly just to emphasize that these are really just low-resolution shapes, giving you a broad outline of the macromolecule. If you're interested in learning more about how this is calculated, you can go read the paper on SAXS. So the clustering is done with DAMMClust if you've selected that option. This essentially looks at the models that you've generated and asks, are there any subclusters within the set? Are there any sets of models that are more similar to each other than they are to the rest of the models? If this is the case, if you come up with several clusters, it's possible that you're trying to reconstruct multiple conformations in the same solution. If something is adopting, say, an open and a closed conformation, maybe you're reconstructing both of those. Finally, onto the summary section. So here you can see there's a summary for each model, 1 to 15. There's the summary of the average and the filtered model created by DAMMAver. Then there's a summary of the refined model created by the DAMMIF refinement based off of the DAMMAver results. The first thing we want to look at is the chi-squared column. Ideally, for every model, this should be similar, close to 1, but not less than 1. In this case, that tends to be true. You can see they're all about 1.2, 1.1. Next, we want to look at the radius of gyration. If you have a good reconstruction and you've done the rest of your analysis well, this should be close to what you're seeing for the Guinea and P of R function. Similarly, the Dmax should be close to what you found with the P of R function. And you can see that it is, especially for the refined model. The excluded volume can be useful, but more, I think, practically useful is the estimated molecular weight from the excluded volume. This should be close to your protein molecular weight. In this case, we're expecting 172. You can see the refined model is actually shockingly close to that. And then finally, in this column, you have the mean NST for the model. The model highlighted in blue is what DAMMAver identifies as the representative model. If you haven't done a refinement, if you haven't done the DAMMIN refinement, this representative model, the one highlighted in blue, is the one that you would want to present as the model for your system. So going on and looking at these individual model tabs again, really all you're looking for here is the normalized residual. It should be flat and ideally randomly distributed about 0. There's also a viewer. This is not very refined viewer, but if you want, you can click and drag to rotate the model. You can left click and drag to zoom in or out. And while it's certainly not PyMol or Chimera or some viewing system like that, it is at least a quick way to get an idea of what the model looks like. In this case, as with many SAXS models, it essentially looks like a potato. So that's everything that we see in the results in the viewer. All this information is saved automatically once the results happen in a spreadsheet, so it's easy for you to grab it and put whatever useful information you need in your publication. So now that I've talked about what we see in RAW, I'm going to go ahead and close this window. I do want to spend a little bit of time talking about the results that we actually get, the output files. So I'm going to open up a file browser, and here you can see a list of the output files from this reconstruction. So we have the prefix, glucose isomerase. This O1 is the model number, so it's going to go from O1 to 15 in this case, because we did 15 reconstructions. So for each model, you get this -1 output. This is the Bead model in PDB format. In addition to that, you also get these fir and fit files. So the fir file, in my opinion, is really the most useful. This gives the fit of the scattering profile from the model against the experimental data. This can actually just be loaded into RAW. For example, we could drag and drop, and then you can see the model fit and the experimental data there. It's loaded into the Profiles tab as two different profiles. There's also the log file, which is what you saw displayed in the log window when we were running the DAMMIF reconstructions. So now, if you've done the DAMMAver DAMMClust, you also see this R file. This is a rotated file. This is the the rotation of the file relative to the chosen central model of the system. So this is actually the model aligned to the central model. I'm going to scroll down now. So if we've done DAMMIF, so what DAMMIF does is it aligns all the files, and then it looks for what the most occupied volume across all the models is. Using that, it creates two different files. It creates the DAMMIF file, which is kind of a larger version of this occupied volume, and it creates the DAMMFilt file, which is a more compressed version of this occupied volume. You can display these models, but generally speaking, neither one actually fits the dataset because they're just the most probable volume based on all the different models, and so they're not really good results to use. It also creates this DAMSO log and DAMSUP log, which contain some of the results shown in the summary tab, and it creates the DAMStart PDB. This DAMStart PDB is what we feed into the refinement to get the refined result if we've done that. If we did clustering, you'll also see a DAMClust log file, which contains the clustering results that we saw in the summary panel. If we did a refinement, in addition to all of this, if we scroll further down, you'll see there's this refined file. So refine underscore, the -1 is the model of interest. We have the same fir and fit files in a log file. If we did the alignment to the high-resolution structure, you'll also see the high-resolution structure is in the folder. And some of the models will have a -aligned version. So for the central model that DAMMIF picked, this one that was highlighted in blue, you see that gets aligned to the high-resolution structure. The DAMMIF model, the DAMMFilt model, and the refined model also all get aligned if they're available. So these models could then be loaded into PyMol, and they would, or Chimera, or whatever your favorite visualization program is, and they would all be aligned to the high-resolution structure of our choice. Finally, I want to note that we have this results CSV and PDF. The CSV is, as I mentioned, all the results in the results summary are saved. I can just open this in Microsoft Excel. And what you'll see is all of the results from the results summary, that table, the clustering, the NSD, the ambimeter, and the input parameters. So what the mode was, the symmetry, number of reconstructions, all of that. This PDF file is just the plots that we saw in the summary panel, saved so that you can easily look at the model fits. That's everything that running the DAMMIF produces. It doesn't save any information with the out file because there's too much information to save, but it does produce all of those results. With that, that's the end of the tutorial. You should now know how to run DAMMIF or DAMMIN from RAW to produce bead models.